Welcome to The Chill Scientist. Today's topic is Jupiter. Let's jump right in. Imagine if Earth went to the gym, chugged every protein shake in the solar system, and bulked up to superhero size. That's Jupiter. It's not just the biggest planet orbiting our sun. It's the heavyweight champion, the cosmic bouncer that makes all the other planets look like scrappy little sidekicks. But Jupiter is more than just a giant ball of gas hanging out in space. It's a stormy, complex, planet-shaping monster that's been ruling our cosmic neighborhood for over 4.5 billion years. And to understand the solar system, you can't ignore the king. Let's start with some numbers. Don't worry, they won't hurt. Jupiter is so massive that you could fit more than 1,300 Earths inside it. If Earth were a marble, Jupiter would be a basketball. Its diameter stretches about 142,000 kilometers, or roughly 88,000 miles, across. Compare that to Earth's humble 12,700 kilometers, or about 7,900 miles, and you start to see just how outmatched we are. And its mass? Jupiter is more than 300 times heavier than Earth. And yet, for all that size, it's mostly empty space. Jupiter is made almost entirely of hydrogen and helium, the same stuff that fuels stars. If Jupiter had been about 75 times more massive, nuclear fusion could have started in its core, and our solar system would have had two suns. Picture that for a second. Twin suns rising and setting across the sky, like something straight out of Star Wars. We're basically living next door to a failed star. Size isn't just for bragging rights. Jupiter's gravity is like a cosmic vacuum cleaner. Its pull is so strong that it shapes the orbits of comets and asteroids, either flinging them away or swallowing them whole. Some scientists even think that without Jupiter, Earth might have been pummeled so relentlessly by space rocks that life would never have had a chance to develop. In a way, Jupiter might be the reason we're here. It's like the solar system's older sibling, sometimes a bit of a bully, but always ready to step in when danger shows up. Here's something wild to think about. If you could somehow see gravity standing on Earth's surface, Jupiter would shine brighter than the sun in terms of sheer gravitational dominance. That doesn't mean you'd float off your lawn chair toward it, but it shows how much sway this planet has across the solar system. Of course, Jupiter doesn't have a surface to stand on in the first place, but more on that later. Even if you've never peered through a telescope, you've probably seen pictures of Jupiter's colorful face. Those orange, brown, and white stripes aren't just for decoration. They're enormous jet streams blasting around the planet at hundreds of kilometers per hour. In miles per hour, that's faster than the strongest hurricanes on Earth. And then there's the planet's most famous scar, the Great Red Spot. This storm is so huge it could swallow Earth whole, and it's been raging for at least 350 years, probably longer. When scientists first spotted it in the 1600s, Galileo thought it might be a blemish on his telescope lens. Nope. It was and still is a hurricane of cosmic proportions, though it's slowly shrinking in size like a balloon losing air. Don't worry though, it's still big enough to make you feel small. And Jupiter doesn't travel alone. Earth has one moon. Jupiter? It's got an entire entourage, over 90 moons and counting. Some of them, like Europa and Ganymede, are so fascinating they could be star attractions in their own right. Europa may have a salty ocean under its icy surface, while Ganymede is the largest moon in the entire solar system. Others are lumpy, potato-shaped rocks caught in Jupiter's gravitational web, orbiting like nameless bodyguards. When Galileo spotted the four largest moons back in 1610, the world flipped upside down. For the first time, people realized moons could orbit something other than Earth. That discovery shattered the belief that we were the center of everything, and it ticked off more than a few important people at the time. Jupiter isn't just a big ball of gas. It's a cosmic laboratory. Its storms, its magnetic field, and its swarm of moons push the boundaries of what we know about physics, chemistry, and even the possibilities of life. Scientists send spacecraft to study it because Jupiter is like a cheat sheet for understanding giant planets everywhere. When astronomers look at exoplanets, distant worlds orbiting other stars, many of them are gas giants that look a lot like Jupiter. By studying the king of our own solar system, we're decoding the rules that apply to planets across the galaxy. You might be thinking, okay, so it's big, stormy, and has a bunch of moons. Why should I care? Fair question. Here's why. Jupiter is part of the reason Earth is even habitable. During the early chaos of the solar system, it helped clear away dangerous debris and stabilize planetary orbits. Without its gravitational influence, the story of Earth and life could be very different or non-existent. On top of that, Jupiter keeps scientists humble. We like to think we've got the universe figured out, but every time we take a closer look, Jupiter throws us a curveball. Radiation belts strong enough to fry spacecraft, storms that defy explanation, auroras that dwarf Earth's northern lights, and moons that practically beg for exploration. Jupiter is like the class clown, who also happens to be the smartest kid in the room. Chaotic, fascinating, and impossible to ignore. Long before telescopes, humans could see Jupiter shining in the night sky, brighter than almost everything else. The Romans named it after their king of the gods, Jupiter or Zeus in Greek mythology. The name stuck, and honestly, it fits. In astrology, Jupiter has always symbolized growth, power, and luck. Priests, sailors, and storytellers throughout history tracked its movements like a cosmic signpost. Even today, Jupiter continues to inspire. In science fiction, it's often a place of mystery, from Arthur C. Clarke's 2001, A Space Odyssey, to countless alien thrillers. It's the perfect mix of beauty and menace, a reminder that space is both spectacular and dangerous. So here's the bottom line. Jupiter isn't just another planet. It's the biggest, baddest, most influential player in the solar system. To understand how planets form, why Earth is safe, most of the time, and where we might find life elsewhere, you have to start with the king. Over the next 7 sections, we'll peel back the layers of this gas giant. We'll dive into its atmosphere, explore its magnetic field, take a tour of its moons, and look at how humans have tried, and sometimes failed, to study it. Along the way, we'll see how a ball of gas can be more thrilling than an action movie. So grab your imaginary space helmet. Things are about to get stormy. If you tried to land a spaceship on Jupiter, you'd have a very bad day. First, you'd aim for that big striped ball in the sky, expecting at some point to hit ground. But the deeper you went, the more you'd realize there's nothing solid waiting for you. Instead of landing, you just keep sinking through layers of gas and crushing pressure until both you and your ship were squashed into atoms. Jupiter isn't a solid world like Earth or Mars. It's made almost entirely of gas, and it's so strange that trying to understand what lies inside is like reading a mystery novel where half the pages are missing. At its core, Jupiter is mostly hydrogen and helium. That's the same recipe that makes up stars. In fact, if Jupiter had been about 75 times more massive, the pressure and heat inside would have been enough to trigger nuclear fusion, the process that makes stars shine. If that had happened, our solar system would have been a binary system, with Earth orbiting between 2 suns. Instead, Jupiter is like a star that didn't quite make the cut, a failed star but an impressive planet. The top layer of Jupiter is its atmosphere, the colorful stripes and bands that we see from telescopes and spacecraft photos. These stripes are made up of hydrogen, helium, and traces of other chemicals like ammonia and methane, which give the planet its colors. But unlike Earth's atmosphere, which is a thin skin over a solid surface, Jupiter's atmosphere just keeps going, thousands of kilometers or thousands of miles deep, gradually blending into the rest of the planet. Scientists often struggle with where to say Jupiter's atmosphere ends and the rest of the planet begins, because there's no clear boundary. As you sink deeper into Jupiter, the pressure ramps up in ways that make Earth look tame. Near the cloud tops, the pressure is similar to what you'd feel standing on Earth's surface. But drop down just 150 kilometers, or about 90 miles, and the pressure becomes several times stronger than Earth's. Go a few thousand kilometers, or a couple thousand miles further, and you're dealing with pressure so crushing that hydrogen gas starts changing into something exotic: liquid. Liquid hydrogen sounds weird, but the real kicker comes deeper still. At around 20,000 kilometers, or about 12,000 miles beneath the cloud tops, the pressure is so extreme that hydrogen atoms are squeezed together tightly enough to behave like a metal. This metallic hydrogen can conduct electricity, and scientists think it's the key to Jupiter's powerful magnetic field, which is the strongest of any planet in the solar system. Metallic hydrogen doesn't exist naturally on Earth, and we can only try to simulate it in labs with massive pressures. On Jupiter, it's as common as ocean water is on Earth. What about a core? That's one of Jupiter's big mysteries. For a long time, scientists thought Jupiter must have a solid, rocky core like Earth, just bigger. Some models predicted a dense core about 10 to 20 times the mass of Earth, buried under all that gas. But new data from NASA's Juno spacecraft has complicated the picture. Juno's measurements suggest that if Jupiter has a core, it's not a neat, solid ball. Instead, it might be a fuzzy core, a messy region where heavy elements are mixed with hydrogen and helium, smeared out over a vast area. It's like a milkshake instead of a bowling ball. This uncertainty makes Jupiter exciting. We tend to imagine planets as simple things: solid rock, icy shell, or ball of gas. But Jupiter reminds us that nature doesn't fit neatly into categories. It's not just gas on the outside and rock in the middle. It's a gradient of changing states of matter, with physics we don't fully understand happening at unimaginable depths. To help picture this, imagine you're diving into the ocean, but instead of finding fish and coral reefs, the water itself slowly changes into something new. The deeper you go, the stranger it gets. At first, the water feels like normal water. Then suddenly, it becomes a thicker, heavier liquid that behaves in bizarre ways. Keep going, and now the liquid has turned metallic, sparking with electricity and glowing with energy. That's what it's like to fall into Jupiter, a transformation zone where matter behaves like nothing you'd encounter on Earth. Of course, you wouldn't survive that fall. The pressure inside Jupiter is measured in millions of Earth atmospheres. Imagine stacking millions of cars on top of you, and you're getting close. Temperatures skyrocket too. At the cloud tops, it's a chilly minus 145 degrees Celsius, or about minus 234 degrees Fahrenheit. But deeper inside, it heats up to tens of thousands of degrees, hotter than the surface of the sun. And remember, this is all without nuclear fusion. Jupiter just generates heat from the sheer energy of its formation and from slowly contracting under its own gravity. That heat is still leaking out today. In fact, Jupiter radiates more energy into space than it receives from the sun. It's like a slow-burning ember, glowing faintly as it sheds leftover heat from its birth 4.5 billion years ago. That's one reason its storms and atmospheres stay so active. The planet isn't just a passive ball being lit by sunlight. It's a dynamic, heat-spewing giant with its own internal engine. This also explains why studying Jupiter isn't just about one planet. Across the galaxy, astronomers have found thousands of gas giants orbiting other stars. Many of them are hot Jupiters, massive planets circling so close to their stars that their atmospheres are boiling. By understanding how Jupiter works, its layers, its metallic hydrogen, its heat, we get a head start in decoding these alien worlds. Jupiter is basically a laboratory sitting in our backyard, teaching us the physics of giant planets everywhere. So while you can't land on Jupiter, and you definitely wouldn't want to try, it's not a disappointment. In fact, the lack of a solid surface is what makes it so fascinating. It forces us to rethink what a planet even is. It's not just a giant marble you can stand on. It's a layered, evolving, sometimes baffling world where matter itself changes character under extremes we can hardly imagine. Earth might be home, but Jupiter is a reminder that the universe doesn't play by our rules. If you could fly above Jupiter in a spaceship, the view would be both beautiful and terrifying. Instead of calm blue oceans and green continents like Earth, you'd see a planet wrapped in swirling bands of clouds, storms bigger than Earth itself, and winds moving at speeds that would make a Category 5 hurricane look like a gentle breeze. Jupiter's face is its atmosphere, and this face is constantly shifting, raging, and pulsing with energy. Those famous stripes you've seen in pictures aren't just random decoration. They're actually enormous bands of gas moving at different speeds and in opposite directions. The lighter colored bands are called zones, and the darker ones are called belts. Zones are cooler and filled with rising gas, while belts are hotter and filled with sinking gas. Imagine standing between two highways where traffic is zooming in opposite directions at hundreds of kilometers per hour, well over 300 miles per hour. That's what happens across Jupiter's atmosphere, but stretched around an entire planet that's 142,000 kilometers wide, or about 88,000 miles. The boundaries between these belts and zones are where the magic happens. They're unstable, chaotic regions where gases mix and churn, creating massive storms. Some of these storms last for weeks, others for centuries. And the most famous of them all is the Great Red Spot. The Great Red Spot is basically a hurricane on steroids. It's a swirling, oval-shaped storm located in Jupiter's southern hemisphere, and it's so huge that Earth could fit inside it with room to spare. Right now, it's about 16,000 kilometers wide, or around 10,000 miles, but in the 1800s, it was almost twice that size. Over the centuries, scientists have watched it slowly shrink, though nobody is sure if it's disappearing entirely or just going through a long-term cycle. What makes it so fascinating is how long it has lasted. Hurricanes on Earth might rage for a couple of weeks at most, but this storm has been recorded since the 1600s. Some scientists think it might have existed for more than 400 years. The winds inside it reach up to 430 kilometers per hour, or about 270 miles per hour. That's faster than any hurricane on Earth. And unlike hurricanes here, which are powered by warm ocean water, the Great Red Spot is fueled by the heat from Jupiter's interior and the incredible energy of its atmosphere. And the Great Red Spot isn't the only storm. Jupiter is covered in them, some nearly as big as Earth, popping up and disappearing in different belts. In 2020, the Juno spacecraft even spotted superbolts, lightning strikes in Jupiter's atmosphere that were up to 10 times more powerful than Earth's strongest bolts. Imagine a lightning storm where every flash could vaporize a skyscraper. That's just a Tuesday on Jupiter. So what are these clouds made of? Unlike Earth's atmosphere, which has water clouds, Jupiter's upper clouds are mostly ammonia crystals. Beneath those, scientists think there may be deeper layers made of water and ammonium hydrosulfide. The colors, reds, browns, whites, and oranges, come from chemical reactions in the upper atmosphere, though no one knows the exact recipe. Some theories suggest sunlight breaks apart ammonia and methane, creating complex molecules that stain the clouds with these wild hues. And then there are the winds. Earth's jet streams blow at maybe 160 kilometers per hour, or about 100 miles per hour, which is already strong enough to make airline pilots sweat. On Jupiter, winds in some bands roar at 540 kilometers per hour, or 335 miles per hour. These winds are so stable and long-lasting that they circle the planet endlessly, giving Jupiter its striped look. Scientists don't fully understand why they're so persistent, but Jupiter's rapid rotation plays a big role. Speaking of rotation, Jupiter spins fast, really fast. It completes one day in just under 10 hours, even though it's more than 11 times wider than Earth. Imagine a planet that massive spinning like a top. That's why its equator bulges outward and why its weather systems are supercharged. The rapid rotation causes something called the Coriolis effect, which twists winds and storms into those swirling patterns that make the planet look like a marble dipped in paint. One of the wildest discoveries from NASA's Juno mission is that Jupiter's weather goes deeper than anyone expected. For a long time, scientists thought the stripes and storms were just a skin-deep phenomenon. But Juno's instruments revealed that these bands extend thousands of kilometers, or thousands of miles, below the cloud tops. That means Jupiter's atmosphere isn't just a thin outer layer. It's a massive, deep, and complex system that dominates the whole planet. To put this in perspective, imagine if Earth's jet streams weren't just a few kilometers tall, but went all the way down to the mantle. That's how extreme Jupiter is. It's not just a planet with some clouds on top. It's a giant machine of gas, pressure, and heat, operating on a scale our planet can't compete with. So when you look at Jupiter's swirling stripes through a telescope or in a spacecraft photo, you're not just seeing pretty patterns. You're looking at jet streams that could rip apart continents, storms that outlast civilizations, and lightning bolts that make ours look like sparks from a lighter. Jupiter's atmosphere is alive in a way that makes Earth's weather look like child's play. And here's the kicker. For all the data we've gathered, scientists still can't fully explain why Jupiter's weather behaves the way it does. Why do some storms last for centuries? Why do the colors change? How deep do the winds really go? Jupiter keeps its secrets close, and every mission only reveals more puzzles. What we do know, though, is that this planet wears its chaos on its face. Its atmosphere is a billboard of power and beauty, reminding us that weather doesn't just happen on Earth. It can be an epic, planet-sized performance. If Jupiter's size and storms weren't already intimidating enough, it also happens to have a magnetic field that makes Earth's look like a fridge magnet. Think about this. Earth's magnetic field is what protects us from the sun's charged particles, creating auroras near the poles and keeping our atmosphere safe. Without it, life here would be in big trouble. Now scale that up by about 20,000 times, and you've got Jupiter's magnetic field, a monster invisible shield that stretches millions of kilometers into space and dominates its corner of the solar system. To picture how big it is, imagine standing outside at night. If Jupiter's magnetic field were visible, it would appear larger in the sky than the full moon, even though the planet itself is over 600 million kilometers, or about 370 million miles, away at its closest. It's the largest structure of any kind in the solar system, second only to the solar wind bubble that surrounds all the planets. So where does this incredible power come from? The secret is metallic hydrogen. Deep inside Jupiter, hydrogen is squeezed under so much pressure that it behaves like a metal, conducting electricity. As Jupiter rotates, remember it spins once every 10 hours, this metallic hydrogen acts like a dynamo, generating a magnetic field so strong it warps space itself. The result is a magnetosphere that dwarfs everything else nearby. And here's where it gets nasty. Trapped inside that magnetosphere are belts of charged particles, like a supercharged version of Earth's Van Allen radiation belts, except Jupiter's are so intense that they could fry spacecraft electronics in minutes if they aren't heavily shielded. For humans, it would be instant doom. Imagine stepping into an X-ray machine and cranking it up to 1,000. That's what it would be like to hang out anywhere near Jupiter's radiation belts. When NASA sent the Galileo spacecraft to orbit Jupiter in the 1990s, the engineers had to design extra shielding to keep its instruments alive. Even then, the spacecraft often had glitches, resets, and occasional data loss because of the radiation frying its circuits. Juno, the spacecraft orbiting Jupiter today, follows a carefully designed path that dives close to the planet for just a short time, and then swings far out again, avoiding the deadliest parts of the magnetosphere. It's like a surfer timing the waves so they don't get slammed into the rocks. But Jupiter's magnetic field isn't just dangerous. It's also breathtaking. When those charged particles slam into the planet's atmosphere near its poles, they create auroras, just like Earth's northern and southern lights. Except on Jupiter, these auroras are permanent, massive, and unimaginably powerful. They're so bright that if you could stand above the planet and look down, they would cover areas larger than Earth itself. They even emit X-rays, which we can detect with telescopes here on Earth. Compared to them, our auroras are flickering campfires, while Jupiter's are raging bonfires lighting up the sky. These auroras also do something unique. They're influenced not just by the sun, but by Jupiter's moons. The most dramatic example is Io, the volcanic moon. Io spews so much sulfur and other material into space that it forms a plasma torus, a giant ring of charged particles that gets trapped in Jupiter's magnetic field. As Io zips through this plasma, it acts like a generator, creating an electric current that flows along magnetic field lines back to Jupiter's poles. The result? Bright spots in Jupiter's auroras that pulse in time with Io's orbit, as if the moon is literally powering light shows on the planet. This connection between planet and moon is unlike anything we see on Earth. Imagine if the moon could trigger extra northern lights in Alaska every time it completed an orbit. That's the kind of cosmic interaction happening at Jupiter. The magnetic field also helps explain why Jupiter has such an enormous influence on its environment. It shapes how particles move around the planet, affects the surfaces of its moons, and even creates radio emissions that we can pick up with radio telescopes here on Earth. In fact, the first hints of Jupiter's powerful magnetosphere came not from spacecraft, but from radio waves detected back in the 1950s. It was like the planet was blasting music across the solar system, and we finally tuned in. And if you're wondering whether this giant magnet could affect Earth, don't worry, we're too far away. But if Jupiter were closer, its magnetosphere would completely dominate our skies. It's not hard to imagine how ancient humans might have told stories about a glowing, stormy god if Jupiter had been a neighbor like Mars. All of this makes Jupiter's magnetosphere both a hazard and an opportunity for exploration. For spacecraft, it's a nightmare zone requiring careful planning and shielding. For scientists, it's a treasure chest of data about how magnetic fields work on a massive scale. And for anyone dreaming about visiting Jupiter's moons someday, it's a reminder that technology will need to be tough enough to withstand a planetary radiation oven. So in the end, Jupiter's magnetic field isn't just the biggest in the solar system. It's a statement. It says, I'm not just big, I'm powerful, and I control everything around me. Between its radiation belts that melt spacecraft, its auroras that outshine Earth's skies, and its moon-powered light shows, Jupiter proves that invisible forces can be just as impressive and just as deadly as giant storms and swirling clouds. Jupiter might be the king of planets, but even kings don't travel alone. Around it swirls an entourage so large that it makes Earth's lonely little moon look like a single roadie following a rock star on tour. Jupiter has over 90 moons. Yes, more than 90. And each one is caught in the giant's gravitational net. Some are nothing more than lumpy, potato-shaped rocks, but others are full-fledged worlds, each stranger and more exciting than the last. If Jupiter itself is a cosmic heavyweight, its moons are the supporting cast that steal the show. The most famous of these moons are the 4 that Galileo discovered in 1610, using a telescope so small and shaky that today you could buy a better one at a hobby store. But what he saw changed human history. He noticed 4 tiny dots moving around Jupiter, and after several nights of observation, he realized they weren't stars. They were moons. It was a scandal in his time because it proved that not everything in the heavens orbited Earth. These moons became known as the Galilean moons, Io, Europa, Ganymede, and Callisto. Each of them is fascinating enough to deserve their own chapter, but let's take a tour. Io is the most volcanic body in the solar system. Imagine a world covered in hundreds of active volcanoes, spewing fountains of molten sulfur miles into space. Some eruptions are so big that they could fit the entire state of Texas inside them. The surface is scarred with lava lakes, mountains taller than Everest, and a constantly shifting landscape. Io is basically what you'd get if Mordor from The Lord of the Rings was an entire planet. The reason it's so volcanic is tidal heating. Jupiter's immense gravity pulls and stretches Io as it orbits, and the nearby moons tug on it too, flexing the crust like a stress ball. All that flexing generates heat inside, and the result is non-stop volcanic chaos. Then there's Europa, which looks calm and smooth on the outside, but hides one of the most exciting secrets in the solar system. Its surface is a shell of ice, crisscrossed by cracks and ridges, looking a bit like someone froze an ocean and then stomped on it. But underneath that ice is where things get wild. Evidence suggests Europa has a vast, salty ocean, twice as much water as all of Earth's oceans combined. And where there's liquid water, there's a chance for life. Scientists think Europa's ocean could be kept warm by the same tidal heating that cooks Io, making it a possible haven for alien microbes, or maybe even something bigger. No wonder future missions like NASA's Europa Clipper are laser focused on this moon. If we ever find life elsewhere in the solar system, Europa might be where it's hiding. Next up is Ganymede, the largest moon in the solar system. Calling it a moon almost feels insulting. Ganymede is bigger than Mercury, and if it orbited the Sun instead of Jupiter, we'd probably call it a planet. It has mountains, valleys, icy plains, and even a magnetic field of its own. The only moon we know of that does. Imagine a magnetic bubble inside Jupiter's already massive magnetosphere. It's like a Russian nesting doll of magnetism. Ganymede likely has its own subsurface ocean too, making it another candidate for life. And if you stood on its surface, Jupiter would loom so huge in the sky that it would make Earth's moon look like a thumbnail. Finally, there's Callisto, the ancient one. Callisto's surface is battered with craters, more scars than any other moon in the solar system. It's basically a fossil frozen in time, showing what the early solar system was like when collisions were common. Unlike Europa or Ganymede, Callisto doesn't have much geological activity, but some evidence suggests it too may have a hidden ocean deep beneath its crust. If Europa is the young, energetic adventurer, Callisto is the wise elder, quietly holding its secrets. Beyond the Galilean moons, Jupiter's satellite system is a messy, beautiful collection of oddballs. Some moons orbit backwards, going against the flow of Jupiter's rotation, suggesting they were captured asteroids. Others are tiny shards just a few kilometers wide, like crumbs left behind from ancient collisions. Amalthea, for example, looks like a giant red potato and orbits so close to Jupiter that it's bathed in deadly radiation. Metis and Adrastea are tiny shepherd moons, guiding the edges of Jupiter's faint ring system. Yes, Jupiter has rings too, not as dazzling as Saturn's, but delicate and mysterious. What's striking is how different all these moons are. In one planetary system, you get a volcanic hellscape, an ice world with a hidden ocean, a giant magnetic planet moon, and a cratered relic. It's like Jupiter is hosting a miniature solar system of its own. If the Sun had vanished and Jupiter had been massive enough to become a star, its moons could have been planets in their own right. And let's not forget how much these moons interact with Jupiter itself. Io's volcanic eruptions actually feed material into Jupiter's magnetosphere, creating glowing auroras on the planet. Europa, Ganymede, and Callisto all feel the tug of Jupiter's gravity, shaping their orbits and possibly keeping their oceans liquid. It's a constant dance with Jupiter as the lead partner pulling everyone else along. For scientists, these moons aren't just side characters. They're front and center in the search for life beyond Earth. The idea that multiple worlds orbiting one planet could each hold oceans or the ingredients for life is mind-blowing. It raises the possibility that life might not be rare at all. If even Jupiter's moons could host it, then maybe the galaxy is full of it. And from a human perspective, these moons spark imagination like few places in the solar system. Picture standing on Europa, watching cracks in the ice glow faintly from the ocean below, while Jupiter towers above you in the sky. Or walking on Ganymede, seeing auroras flicker across the horizon. Or orbiting Io, watching fountains of lava burst into space like fireworks. These are the kinds of places that make exploration feel less like science and more like adventure. Jupiter itself might be too hostile for humans to ever visit up close, but its moons, they're the future playground of explorers, scientists, and maybe, one day, colonists. They remind us that even orbiting a single planet, the universe can deliver an entire catalog of wonders. When scientists discuss where life might exist beyond Earth, Jupiter itself rarely makes the list. Its crushing pressures, violent storms, and intense radiation rule it out as a candidate. But its moons, especially Europa, Ganymede, and Callisto, tell a different story. These icy worlds may contain vast underground oceans and the ingredients necessary for biology. While the surface of Jupiter is inhospitable, the region around it could hold some of the most promising environments for life in the entire solar system. Europa has become the leading focus of this search. Its surface is a shell of ice tens of kilometers thick, crisscrossed by ridges, cracks, and chaotic terrain that appear to have formed by movement within the ice. Beneath that shell, evidence strongly suggests the presence of a global liquid ocean. This ocean could be as much as 100 kilometers, or about 60 miles deep, making it more than twice the volume of all Earth's oceans combined. Importantly, this ocean is thought to be in contact with a rocky seafloor. On Earth, such environments support hydrothermal vent ecosystems, rich with life that use chemical energy rather than sunlight. The same kind of chemistry might take place on Europa. There are also signs that Europa's ocean interacts with the surface. The Hubble Space Telescope has observed what appear to be plumes of water vapor erupting from the surface and shooting into space. If confirmed, these plumes could provide an extraordinary opportunity. Spacecraft might be able to fly through them and directly sample the ocean without drilling through the ice. Chemical analysis could then reveal whether the water contains organic molecules or other signs of habitability. Ganymede, the largest moon in the solar system, also likely harbors an ocean beneath its icy crust. Unlike Europa's, Ganymede's ocean may be buried between layers of ice, making interaction with the rocky core less direct. That could make it less favorable for life, since many scientists believe the contact between water and rock is critical for generating chemical energy. However, the sheer size of the ocean is compelling. Some models suggest Ganymede's ocean could be hundreds of kilometers deep, containing far more water than Earth. Ganymede's magnetic field, unique among moons, hints at a dynamic interior that may help sustain this ocean. Callisto, though heavily cratered and geologically quiet, may also have a deep ocean beneath its surface, as indicated by measurements of its magnetic environment. If present, this ocean would be buried much deeper than those of Europa or Ganymede, making it less accessible and perhaps less likely to support life. Still, Callisto's environment is important for another reason. It lies outside Jupiter's harshest radiation belts, making it one of the safer targets for long-term human or robotic exploration. Io, the fourth Galilean moon, is dominated by volcanism and constant resurfacing. Its environment is shaped by lava, sulfur, and radiation, which makes it extremely unlikely to support life. While scientifically fascinating, Io is not considered a candidate for habitability. The possibility of life in Jupiter's system is not limited to the moons. A few scientists have speculated that microbial life could exist in the upper atmosphere of Jupiter itself. where temperatures and pressures briefly resemble Earth-like conditions. However, the turbulence, radiation, and lack of stability make this highly speculative. The moons remain the primary focus. Upcoming missions will soon investigate these worlds in greater detail. NASA's Europa Clipper, scheduled to launch in 2024 and arrive at Jupiter in the early 2030s, will perform around 50 flybys of Europa. Its instruments are designed to map the surface, measure the thickness of the ice, analyze the composition of the surface and atmosphere, and search for active plumes. Clipper carries spectrometers to detect organic compounds, ice-penetrating radar to probe beneath the crust, and cameras to capture Europa's terrain in unprecedented detail. If plumes are active, Clipper may fly through them to directly sample material from the subsurface ocean. The European Space Agency's JUICE mission, Jupiter Icy Moons Explorer, launched in 2023 and will arrive at Jupiter in 2031. JUICE will study Ganymede in particular, as well as Europa and Callisto. It will examine their surfaces, search for subsurface oceans, and measure magnetic fields and plasma interactions. JUICE will eventually enter orbit around Ganymede, becoming the first spacecraft to orbit a moon other than Earth's. This will allow extended study of its geology, ice, and magnetic field, offering critical insights into its potential for habitability. Looking further ahead, concepts for landers have been proposed. A Europa lander, if funded, could attempt to drill into the ice, or at least analyze surface samples for chemical signs of life. Another idea is a robotic submarine capable of melting through the ice and exploring Europa's ocean directly, though such missions are likely decades away due to the immense technical challenges. Callisto has been suggested as a potential base for human exploration, since its low radiation environment makes it far more feasible than Europa or Io. From such a base, humans could control robotic probes sent to the other moons. The implications of these missions go beyond Jupiter. Exoplanet surveys have revealed thousands of giant planets orbiting other stars, many of which are similar to Jupiter. If Jupiter's moons contain oceans and potentially life, then it is reasonable to assume that exomoons around distant planets might do the same. This expands the concept of habitability from a narrow focus on Earth-like planets to a much broader range of environments where moons of gas giants may be just as promising. Finding life in one of Jupiter's oceans would be a discovery of immense significance. It would prove that life can arise in conditions very different from Earth's surface, supported not by sunlight, but by internal energy and chemistry. It would suggest that life is not a rare occurrence, but a natural outcome wherever liquid water, energy, and the right chemistry are present. Even if no life is found, the results will be just as important. Understanding why these oceans are sterile would help define the true limits of habitability. The search for life around Jupiter is one of the most ambitious goals of planetary science. Within the next 2 decades, the data returned by Europa Clipper, JUICE, and possibly future missions will transform our understanding of these worlds. Whether they prove to be lifeless or harbor thriving microbial ecosystems, the answer will reshape how we see life's place in the universe. When Galileo first pointed his simple telescope at Jupiter in 1610, he saw more than just a bright dot in the sky. He noticed 4 smaller dots moving night after night around the planet. These turned out to be moons, now called the Galilean moons, and the discovery shook the foundations of astronomy. Until then, many people believed that everything in the heavens revolved around Earth. Galileo's observations provided direct evidence that this was not true. It was the first step toward understanding the solar system as we do today, with planets orbiting the sun and moons orbiting planets. For centuries after Galileo, Jupiter remained a mystery viewed only through telescopes. Astronomers could see the stripes, the great red spot, and even hints of shadows when its moons passed in front of it. But the real breakthroughs came with the space age. In 1973, Pioneer 10 became the first spacecraft to fly past Jupiter. It was followed by Pioneer 11 a year later. These missions provided the first close-up images of the planet, showing its atmosphere in detail and giving us the first measurements of its radiation environment. They also revealed that Jupiter had a thin ring system, something that had never been detected from Earth. In 1979, the twin Voyager spacecrafts flew past Jupiter and sent back images that astonished scientists and the public alike. The Voyagers revealed the incredible diversity of the Galilean moons, Io's active volcanoes, Europa's cracked ice shell, Ganymede's grooved terrain, and Callisto's ancient craters. The images of Io erupting lava fountains into space were especially groundbreaking, proving that the solar system was far more active than anyone had expected. Voyager also gave us the best views yet of the Great Red Spot and other storms raging across Jupiter's atmosphere. After Voyager, the next major mission was Galileo, launched in 1989 and arriving at Jupiter in 1995. Unlike the earlier flybys, Galileo entered orbit around Jupiter and stayed there for 8 years, making dozens of close passes by the moons. It confirmed the existence of subsurface oceans on Europa, Ganymede, and possibly Callisto. It also studied Io's volcanoes in detail, mapped the planet's radiation belts, and observed its auroras. Galileo even dropped a small probe into Jupiter's atmosphere, which descended for about an hour before being crushed by the pressure. The data showed strong winds and a surprisingly dry atmosphere, challenging models of Jupiter's structure. Galileo's mission ended in 2003 when it was deliberately directed into Jupiter to avoid accidentally contaminating Europa with Earth microbes. After Galileo, smaller missions continued to add pieces to the puzzle. The Cassini spacecraft, on its way to Saturn in 2000, flew past Jupiter and captured detailed color images of its atmosphere and rings. New Horizons, en route to Pluto in 2007, also used Jupiter for a gravity assist and gathered data on the planet's magnetosphere and moons. Today, Jupiter is being studied by NASA's Juno spacecraft, which arrived in 2016. Juno's mission is focused on the planet itself, especially its interior structure and magnetic field. To survive Jupiter's harsh radiation, Juno follows a highly elliptical orbit, diving close to the planet for a few hours and then swinging far out again. This allows it to make repeated close passes while minimizing damage to its instruments. Juno has already revealed that Jupiter's Great Red Spot extends far deeper into the atmosphere than expected, that its magnetic field is far more irregular than Earth's, and that its core may be fuzzy rather than solid. It has also captured stunning images of Jupiter's poles, showing swirling storms arranged in geometric patterns unlike anything seen before. Juno continues to operate today, with its mission extended to study not only the planet but also flybys of Ganymede, Europa, and Io. The future of Jupiter exploration looks just as exciting. NASA's Europa Clipper mission is scheduled to launch in 2024 and arrive in the early 2030s. It will focus on Europa, mapping the surface, searching for plumes, and investigating its habitability. The European Space Agency's JUICE mission, launched in 2023, will arrive at Jupiter in 2031. After studying Jupiter and its moons, it will eventually enter orbit around Ganymede, the first time a spacecraft will orbit a moon other than Earth's. These missions will carry advanced instruments capable of detecting organic molecules, probing beneath the ice, and analyzing the environments where life may exist. Each mission has built on the ones before it, gradually transforming Jupiter from a distant light in the sky to a dynamic world filled with storms, radiation belts, and moons with hidden oceans. Galileo's simple telescope revealed the first hints. The Voyagers showed us diversity. Galileo, the spacecraft, confirmed oceans, and Juno is now unlocking the mysteries of the planet's interior. Europa Clipper and JUICE promise to push us even further, bringing us closer to answering the question of whether life exists beyond Earth. Jupiter has been observed for over 400 years, yet each mission continues to show us something new. For every question answered, more appear. Why do some storms last for centuries? How exactly does the magnetic field work? What is happening deep within its atmosphere? And most importantly, could life exist on one of its moons? The exploration of Jupiter is far from finished, and in many ways, it feels like we are still only at the beginning. Jupiter is not just another planet in the solar system. It is a cornerstone of how the solar system formed, how it works today, and how we imagine our place in it. Its immense mass, more than twice that of all the other planets combined, makes it a gravitational powerhouse. Without Jupiter, the solar system as we know it would be unrecognizable. During the early days of the solar system, Jupiter's gravity shaped the orbits of countless asteroids and comets. Some scientists believe it helped protect Earth by deflecting dangerous impacts, pulling comets inward only to sling them back out or absorb them entirely. At the same time, Jupiter may have caused chaos, scattering small bodies that later collided with the inner planets, possibly even delivering water to Earth. In this way, Jupiter has acted both as a shield and as a catalyst, influencing Earth's habitability billions of years before life appeared. Its gravitational dominance continues today. Jupiter controls the asteroid belt between Mars and itself, keeping it from forming into another planet. It also hosts large groups of captured asteroids called Trojans, which share its orbit around the Sun. These objects are ancient leftovers from the early solar system, preserved by Jupiter's influence. By studying them, scientists hope to understand the ingredients that built the planets. NASA's Lucy mission, currently underway, will visit several Trojan asteroids, further extending Jupiter's role in planetary science. Jupiter also shapes the environment of its moons in ways no other planet does. Its massive magnetosphere, radiation belts, and tidal forces create extreme conditions that drive volcanism on Io and maintain the oceans of Europa, Ganymede, and possibly Callisto. This makes the Jovian system a natural laboratory for studying planetary processes on a scale far beyond Earth. Beyond science, Jupiter has always held a special place in human imagination. Bright in the night sky, it was observed by ancient civilizations long before telescopes. The Babylonians associated it with their god of justice. The Romans named it after their king of the gods, and cultures across the world recognized its prominence. Even today, its presence inspires both professional astronomers and casual stargazers. To look at Jupiter through a backyard telescope and see its stripes and its 4 brightest moons is to share an experience with Galileo over 400 years ago. The impact of Jupiter on our imagination is also tied to its sheer scale. It is difficult to comprehend a planet so large that it could fit over 1,300 Earths inside it, or a storm like the Great Red Spot that has raged for centuries. It stretches our sense of what is possible in nature, reminding us that the universe is filled with extremes beyond anything on Earth. Jupiter's exploration has also become a symbol of human curiosity. From Galileo's shaky telescope to spacecraft like Juno, sending back high-resolution images of swirling clouds, each step represents a leap in technology and in understanding. The upcoming missions to Europa and Ganymede may one day confirm whether life exists in their oceans, a discovery that would change our view of the universe forever. The search for life around Jupiter is not just a scientific question, it is a philosophical one, tied to the oldest human questions about whether we are alone. Looking to the future, Jupiter and its moons are likely to remain central to space exploration. Robotic missions will continue to probe its atmosphere, magnetosphere, and moons. Human exploration may one day target Callisto, using it as a base of operations for studying the Jovian system. Its moons could eventually become stepping stones for deep space exploration, much as the Moon is today for Earth. Jupiter shows us that the solar system is not a collection of isolated objects, but a dynamic system shaped by interactions of gravity, radiation, and geology. It demonstrates that habitability can exist in unexpected places, not only on Earth-like planets, but also beneath the icy crusts of distant moons. It challenges our technology with its radiation belts and rewards us with discoveries of oceans, auroras, and storms. In the end, Jupiter is more than a planet. It is a reminder of the vastness of the cosmos and of humanity's ability to reach beyond what we can see with the naked eye. From Galileo's first observations to the spacecraft orbiting it now, Jupiter has been a constant partner in our quest to understand the universe. It has shaped our solar system, it may shelter life in hidden oceans, and it continues to inspire wonder. The story of Jupiter is not finished, and as we send new missions and build new telescopes, it will continue to unfold, drawing us deeper into the mysteries of the largest planet in our solar neighborhood.